Good morning, everyone, and welcome to the July 2024 edition of the Southeast Monthly Climate Webinar, where we talk about the climate and special topics pertaining to the Southeast region. My name is Chris Furman. I'm the Deputy Director of NOAA's Southeast Regional Climate Center, and I'll be giving a climate overview of the past month. Our other speakers today are Todd Hamill from the Southeast River Forecast Center, who will provide a water resources update, Pam Knox from the University of Georgia, who will provide an agricultural impacts update. Joining us today, we're pleased to have Dr. Peter Crank from the University of Waterloo, who will be discussing urban heat, the role of buildings, shade, and green infrastructure on urban heat islands. So again, thank you all for joining us. Just a reminder to type those questions and comments into the question box at any time, and they'll be answered at the end. Also, a recap email of this webinar will be sent out with a YouTube link to the recording in the next day or so. All right, let's get started with an overview of the climate. So once again, temperatures over the past month were above average across the Southeast, especially across the interior and northern portions of the region, where some locations were running 5 to 6 degrees above average. And we can also see the temperatures were once again above average across Puerto Rico and the U.S. Virgin Islands. All right, next slide, please. So we can put some of these temperatures into perspective, especially those that reached or exceeded 100 degrees. The map there on the left is a count of the number of days so far this year that have reached or eclipsed the century mark. And you can see that several locations extending from central Florida all the way up to the mid-Atlantic have seen multiple days of 100-degree temperatures so far this year. There are two places that are especially noteworthy that I'll highlight here. There at the top, you can see Washington's Reagan Airport. They recorded 4 consecutive days of temperatures of 101 degrees or higher between July 14th and the 17th. And this broke the previous record of 3 consecutive days that was set back during the Dust Bowl of the 1930s. A little further south, we see that Raleigh-Durham, North Carolina, recorded 3 consecutive days of temperatures of at least 101 degrees between July 4th and 6th, and this is the longest such streak in over a decade. However, what's more notable is that RDU recorded its all-time highest temperature of 106 degrees on July 5th, breaking the previous record of 105 that had been set 6 times previously in a record going back to 1887. The heat index on this day also topped out at over 117 degrees at RDU, which broke the previous record of 115 degrees set just this past August, and that's in a record going back to 1945. So far this year, RDU has recorded 9 days with temperatures of at least 100 degrees, which is tied with 2012 for the most such days through the first 200 days of the year. Okay, next slide. So as is often the case during the summer, precipitation was quite variable across the region over the past month. The wettest locations were found across the central portion of the region, extending from the northern Gulf Coast up to eastern Virginia, as well as in parts of South Florida. In contrast, dry conditions continued to plague much of the interior and northern portions of the region, while the eastern portion of the Florida Peninsula, which saw above average precipitation in June, saw mostly below average precipitation over the past several weeks. Rainfall has also been near normal across most of Puerto Rico. Unfortunately, we still lack a lot of precipitation data across the U.S. Virgin Islands, though some CoCoRaHS gauges on St. Croix recorded 2 to 3 inches over the past month. And if we look on St. Thomas and St. John, some of those gauges have recorded upwards of 5 to 7 inches over the past month or so. Okay, next slide. So as we've done before, if we look at the month-to-date temperature rankings on the left, we see that once again, several stations across the region are on track to record one of their warmest Julys on record, while some stations across northern Virginia, southern Georgia, and South Florida are on track to record their warmest July and perhaps warmest month on record. Same holds true for Puerto Rico, where San Juan is off to its warmest start to the month on record, as is St. Croix. Looking at rainfall there on the right, we see some locations across interior and northern portions of the region, as well as parts of South Florida, are on track to record one of their driest Julys on record, while rainfall remains variable across Puerto Rico and generally above average across the U.S. Virgin Islands, at least according to the available CoCoRaHS data. Since we're also more than halfway through the summer season now, we're starting to track some season-to-date rankings. And if you look at places like Atlanta, Chattanooga, Raleigh-Durham, Punta Gorda, Roanoke, Washington, D.C., and San Juan, they're all on track to record their warmest summer on record, while places like Charlottesville, Bristol Tri-Cities, Lumberton, North Carolina, Washington, D.C., and Chattanooga are also on track to record perhaps one of their driest summers on record. Okay, next slide. So while some places have picked up some decent precipitation amounts over the last couple of weeks, most of the region has been rather dry, especially if we look back to the early part of June, when the faucet that was wide open for most of the winter and spring was abruptly shut off. And as we've seen, temperatures have been above average as well, and that has caused drought conditions to emerge and deteriorate quite quickly over the past month or so. Back in early to mid-June, we can see that there on the left outside of the Florida Peninsula, the region was basically drought-free, had some areas of abnormal dryness scattered about. But as we can see, that pattern has changed considerably, with conditions in South Florida improving, while conditions elsewhere deteriorated, and in some cases by several categories. This is especially the case across parts of northern Alabama, southern Tennessee, parts of the Carolinas, and western and northern portions of Virginia, where severe and extreme drought has recently emerged. Virginia, in fact, recorded its driest June on record just this past month. NIDIS and its regional partners, some of you may have seen this, they issued a detailed update last week on the rapidly deteriorating drought conditions in the region, and you can access that report at the link there at the bottom of the slide. It will also be available in the webinar recap as well. Okay, next slide. And looking in the Caribbean, where they've had quite a bit of rain over the last few months, we see that the region is still free of any drought or abnormal dryness. Okay, next slide. So as we saw last month, ENSO neutral conditions are now present in the equatorial Pacific. Forecasters at CPC are still expecting a transition to La Nina to occur over the next few months as ocean temperatures in the Niño regions continue to cool and the easterly winds ramp up. Specifically, there's a 70% chance of La Nina emerging sometime during the August to October period, and an almost 80% chance of it persisting into the upcoming winter. Okay, next slide. All right, so as we look over the next 3 months, we see that above average temperatures are favored across the southeast region, while above average precipitation is also favored just about everywhere except most of Tennessee and extreme northern Alabama. Okay, next slide. If we look at the Caribbean, we see above average temperatures and precipitation continue to be expected for the rest of the summer and into early fall. Next slide. Looking at the seasonal drought outlook, we see based on, again, that expectation of above average precipitation, drought removal or improvement is forecasted across the region. And at least for now, no new development is expected across the southeast and also the Caribbean as well. All right, next slide. Looking ahead to this weekend and early next week, above average temperatures are likely across the northern and southern tier of the region, while above average precipitation is expected across most of the region except Virginia. Next slide. And if we look out to 2 weeks, as we round out the month of July, we see a continuation of above average temperatures across the northern and southern tier of the region, as well as much of the middle tier of the region. Above average precipitation is expected across nearly all the southeast, except maybe parts of extreme South Florida. Additionally, over the next couple of weeks, the CPC is forecasting a slight risk for excessive heat across northern Virginia. And at this time, there's no risk for rapid onset or flash drought across the region, but of course that could change. So keep your eye on that. Next slide. And finally, as we look ahead to next month, we see that above average temperatures are expected across the region, as are above average precipitation amounts. All right, next slide should be the summary. Yep, here's the summary for you to look over after the webinar. Happy to answer questions at the end. Also want to acknowledge William Schmitz, our service climatologist, who helped compile much of this information. Appreciate his efforts. And with that, I'll turn it over to Todd.
Thank you, Chris. Well, you know, last month it was pretty straightforward. You know, we were getting hot, we were really dry at the end of June. But this briefing is going to be maybe a little slightly more complicated, just because the things have kind of started changing, and Chris kind of alluded to that as he was talking about it. So let's go to our first slide, and this is from the USGS, and it's our 28-day average stream flow. And while the 28-day average does, you look on the left-hand side where it shows each of the different stations and the 28-day average for the comparison to this time of year, you can see that we've got some below normal in some places and some above normal in some places, and that's the hit and miss, kind of the hit and miss of summertime convection in the southeast. And overall, on the right-hand side, kind of shows the duration hydrograph and how quickly we went from being above average across the Southeast at the end of May and beginning of June, and how that dryness really impacted the Southeast, where we've dried out very, very quickly, which isn't terribly unusual, maybe a little bit unusual as we went from wetness to that being that dry. I think the heat played a large role in that too, in the stream flows, and that it dried things out more quickly and showed it just did it very, very quickly, and that's why they call it a flash drought. It happened because it happened so fast. So let's go to the next slide, and the next slide will, instead of doing the 28-day averages, I went ahead and showed the 7-day average stream flow, and that kind of shows a little bit more of the variability from week to week, as opposed to kind of the longer term drought. This kind of looks at it a little bit differently. So let's go ahead and take a look at Alabama, and you can see as with the 28-day average how quickly we went down. Well, the same can be said for each of the different state outlooks or state look back at what happened to the stream flow in the Southeast, and you can see how dry it was. But it doesn't take that much to start to see some variability in the week to week. As we start to see these pop-up thunderstorms, and some of them are more widespread, we get a little bit of a feedback loop, and getting more moisture to the ground, more moisture in the air. So we're going to start to see those rainfalls being a little bit more impactful to the rivers and the streams. And so that's our concern going forward, is that, as opposed to, we really weren't worried about any type of flooding in the last month or so, because it had been so dry and so hot. Well, that's kind of changed now as we start to see these showers and thunderstorms pop up, and we start to wet the soils, and we start to prime the pump. And then we worry about what we get into if we stay this way, where we start to stay wet, if we get tropical systems move into the area. So, but we'll go through each of the states and then talk a little bit more about that. Excuse me. And so we looked at Alabama. We look at Georgia, the same thing, dried out very quickly, but it doesn't take that much to start getting those to jump up and jump into the normal. And we'll start seeing those fluctuations as we go through. And Florida has really gone back and forth. They're in their wet season now. And so we've been wet, but they've actually been dried the last week or so. And so they have actually dried out just a little bit and are getting close in the statewide to being below normal. So let's go ahead and go to the next slide. And then we get to South Carolina, and you see a similar pattern where they've been in the dry, but we're starting to see some fluctuations back into the normal period. And the same with North Carolina, where it is normal now, where we've had just some very recent rainfall that's brought some areas that we were concerned that we might start to see some flooding in that area. But it hasn't happened. We're still in that normal category, but we are priming things for if we do start to see those heavy rains, we could see some flooding in those areas. And the same for Virginia. It's very similar to what North Carolina is. So let's go ahead and go to the next slide. So right now, we have no points in flood in the Southeast. Again, for it seemed like for years, we had points in flood all through the Southeast. At some point, there was some place in the Southeast, but for the last couple of months, because of the dryness, after our El Nino winter, we've actually gone to neutral and things have quieted down. We've been hot and we've been dry. So we have not seen any flooding in the Southeast really in the last month. So let's go ahead and go to the next slide. So we're in week 30 of this year. And so while we talk about not being in flooding, this is the time of year when we wouldn't expect as much flooding. We always talk about it. There could be potentially be flooding during any time of the year, but we're out of our flood season. We're in between our major flood seasons, which is our winter recharge season and our tropical season, where we tend to see flooding. And so we're in week 30 of the year, and so we're kind of in that lull between those two periods, and it continues to be quiet. But we are looking for an active season, and that's part of the reason for the above normal rainfall potential from the Climate Prediction Center. Looking at that, that's kind of their impetus for showing an above normal rainfall for the Southeast is that we are looking for an active hurricane season this year. So that's what part of the reason that we're looking for chances for above normal. So that could make this, we could be heading into a very active part of our flooding season, and it could alleviate a lot of those drought issues. We have to consider that tropical moisture is part of our climatology. And so what it's usually, as we get into fall, it's usually kind of dry, but that tropical moisture helps keep us from getting into those droughts. So let's go ahead and look at Florida here in the next slide. So we're really ramping up in Florida. This is when we would expect to see more of the flooding in Florida. And while things have improved and things are in better shape, certainly in Florida, we've seen the fluctuations in there. This is the time when we would expect the most flooding through Central and South Florida. And we are starting to see plenty of rain in there. And that's why all the drought has been removed from the last one to this one. We've seen plenty of rainfall. We just haven't seen a whole lot of flooding there. We've had enough rain to improve conditions, but not necessarily to have flooding. So that's good news. So let's go ahead and go to the second to last slide. I think this is my last slide. And so really, because I would have normally gone with below normal chance for flooding, but we don't typically expect flooding this time of year. So it's a normal risk for river flooding, especially since we've started to see the rainfall patterns change. And since those patterns have changed, we're starting to see some wetness in the Southeast. And with an active hurricane season right around the corner, that ramp up doesn't really start until the middle of August. And then it really does ramp up through September and then into October. So as we start to look to next month, we'll start to see more potential for heavy rains and flooding in the Southeast. It will be more focused, likely from a tropical system of some sort that would move through. If we continue to see the type of rainfall we're seeing now and don't get a tropical system, we might not see much flooding at all. So that's kind of the reason for the normal risk for river flooding in the Southeast. So let's go ahead and go on to our last slide. And this is just my summary. And you'll get a chance to read this later, and we'll go ahead and move on and let Pam give us a chat.
All right, well, thank you, Todd. Good morning, everybody. We're going to look at a few agricultural impacts. I imagine there's probably not a lot of farmers on the call today because they're probably out in the fields working, but they'll see this later. Let's jump right in. Some of the impacts on agriculture we've seen. The return to reindeer conditions has improved a lot of fields and pastures, but it's just, like putting a match to the fungal diseases like white mold on peanuts. So they're really seeing increases in that, and it really depends on putting timely applications of fungicide and other chemicals on the plants. Because it's rainier, it's a little harder to get into the fields, and so that's been a concern for some farmers. Dryland corn has not done well because it was so dry during most of June and early July. A lot of people were dry through the pollination period, and if the silk is dry, the pollen doesn't stick to it, and you lose the whole crop in just a few days. And so there are some fields that are really beyond being able to harvest anything this year, but there's other ones, especially the irrigated ones, that did better, and so we're really looking to see what happens with those. Dry conditions have been favorable for outbreaks of fall armyworms. We're really starting to see those pop up now across the region, and they're doing quite well, and I know it's a real concern for hayfields and pastures. Because of the dry conditions earlier in the month, the farmers were able to catch up on a lot of field work because they didn't have those really wet conditions. That is starting to change now, and if you look at the forecasters, you can hardly find a 24-hour period where it's not raining, and so that's really an issue because it's just harder to get in if you need to do field work. Obviously, it's good for the moisture conditions. Irrigated corn has been a little ahead of the usual development because of the hot weather, and so they're getting close to harvesting in some cases. And peaches are still being harvested in South Carolina and in Georgia. There's been some issues with scale and other insects. Generally, it's been really good this year, especially compared to last year when they lost so much of it due to the frost. So let's go on. Here's the recent soil temperature and soil moisture. You can see on the left, soil temperatures have been consistently above normal, not nearly as much as some other parts of the country, but definitely keeping things warm because of all the warm temperatures we have. It's cooled off a bit since we're getting a lot more clouds now. But those really, that does affect the plant physiology. And so that's something that we keep in mind. Also, because it's been dry, it's easier for the soil to heat up. And on the right-hand side there, it's the 20 centimeter soil moisture. You can see how spotty it is over the southeast. Really depends on where those storms go. Yesterday's winter was Savannah, where they got almost 4 inches in 2 hours. And, you know, there's other places nearby that basically got nothing. And so that's one of the things about summertime rain. You know, you get these storms pop up. There's not a lot of steering current, so they're really not moving very much. And some areas can get hit by very hard rains. Well, places that are not that far away stay dry. And so the drought monitor has trouble capturing all those short spatial variations in rainfall. And so they just try to do sort of a general overview of that. If we go on to the next slide. Last month, I talked about flash drought or rapid onset drought, and the new indicator that NOAA has, it is gone from the southeast because we've switched this pattern, and now we're in this more daily kind of rainfall. The likely flash drought has moved to the northern plains and the western corn belt, so we don't really seeing that now because temperatures have dropped and we're getting a lot more frequent rainfall. This shows the departure of rainfall for the last 30 days. And you can see how spotty it is across the region, with a number of places getting more than 8 inches above normal for the last 30 days, and other places below normal, especially if you look at northern Georgia and Alabama, and in most of Tennessee, they are really dry because they have not experienced a lot of the rain that we have in other parts of the region. And the drought monitor does show a slower response to dry conditions because they look more at long-term indicators. You can see the timeline there on the bottom shows the percent of the southeast that's been in these different categories of drought. Yellow is abnormally dry, and then as you get darker colors, it gets to be more severe drought. That will probably decrease in the next one because we have been getting more rain, and so the averages are going to kind of just wash out, and so the drought monitor is likely to improve over the next few weeks as we get more of this rain. Let's go on. The dry conditions do a lot of field work. I just compared here percent of normal precipitation on the left for June, and you can see how dry it was across almost the entire region, except for southern Florida, which got hit by some not a tropical storm, but it's definitely tropical rainfall that caused a lot of problems down there. But the rest of the region was really dry. That was what caused a lot of the problems for the corn and other dryland crops. But since then, the last week I showed here on the right-hand side, you can see almost all of the region has gotten well above normal precipitation. Some of this isn't really catching all the variability that we have from those small storms that move around, but you can see generally over time, we're getting a lot more rain. Causes its own problems, but I think in general, farmers prefer to have more rain rather than less. If we go on, the growing degree days, because it's been warmer than normal, we are above the last year for sure. Last year is the blue curve on there. We're right about the long-term average for degree days, and so probably just a little bit above that. If you want to monitor that for your own area, you could use the agroclimate tools, and that will help you. You can put in your own planting date and when you expect to harvest and see where you are on that graph. If we go on, here's my summary, and you can see it's overall, farmers are busy, hard at work, and enjoying the summer if they have time to think about it, I'm sure. But I want to stop here and I'll let you read that later. And now I'm pleased to introduce our special guest, Dr. Peter Crank, who's going to be talking about urban heat island impacts.
Thank you so much, Pam, and thank you all for taking the time to listen. So we'll shift a bit from the rivers and the farmland and agriculture and move into a a little bit about the urban areas as I talk today. So as a brief introduction to myself, I got my PhD at Arizona State University in the southwest part of the US in geography. Prior to that, I was at Mississippi State University in the meteorology and climatology programs there for my undergrad and my master's. But I have spent the past almost decade now looking at extremely hot locations, and particularly the hot cities. So Arizona State is located next to Phoenix, Arizona, which routinely breaks 110, has been up near 115 the past couple of weeks. And then I moved from there to, from the dry heat to the incredibly wet heat of Singapore. And I'll share a little bit of that later on today as well. But we are in that area thinking a lot about how we deal with both extreme heat and extreme humidity. And then recently in the past year, I've moved back to North America, and I'm at the University of Waterloo, which is in southern Ontario in Canada. So if you look at a map, it's the part of Canada that sits in between Michigan and New York, surrounded by the Great Lakes. So even though it is extremely far north, it's also a very humid place, particularly in the summer, and so it also deals with some heat issues along the way as well. So a brief outline for where we're heading today. I'll talk a little bit about what urban heat islands are and give a brief definition to them. I'll also mention some of the risks and symptoms in terms of health that we see for urban heat. And then I'll spend a little bit of time doing somewhat of a crash course in the built environment and how urban climatology helps address those challenges. And then we'll spend a little bit of time looking at examples of how shade and green infrastructure can be used to mitigate urban heat. And then a few key takeaways at the end about the risks associated with urban heat. So when we think about urban heat islands, you may have seen that on the news before in terms of talking about them, but what exactly are they? So cities, most fundamentally, the definition for an urban heat island is that temperatures in an urban area are warmer than their rural surroundings. There are different ways of measuring this, and toward the end of the crash course, I'll give a couple of examples of different types of urban heat islands. But we've known about urban heat islands for a long time now. Originally, it was discovered or identified in London in 1833. And then in 1855, researchers and scientists in Paris noted it there as well and said that human respiration and chimney smoke are causing rust-colored skies and warmer temperatures of about 1 degree Celsius, so nearly 2 degrees Fahrenheit. But it isn't happening just in the big cities of Europe. It happens here in the North American continent and even in our smaller cities in the southeastern part of the US. And all of this, regardless of the size of the city, the climate and the urban heat have significant implications on human health and human activity, again, regardless of what scale of city we're looking at, from Paris in France all the way down to smaller cities such as places like Macon, Georgia. So if that's happening, why should we really care about urban heat or urban heat islands? We know it's hotter, so that's just the way it is. We can deal with that and move on. The challenge is that people live in these urban areas, and that heat then translates into health implications. So this is a slide. There are very similar ones in the US. I just happened to pull one from Manitoba in Canada of what the signs and symptoms are for heat stress. So you can have varying levels of heat stress before you actually reach these medical definitions of heat exhaustion or heat stroke. But I want to pause here because this impacts not just urban areas, but also rural areas as we see extreme heat and extreme humidity. Heat exhaustion and heat stroke become more likely in the general population. So for heat exhaustion, things like faintness or dizziness, excessive sweating, skin being particularly cool, pale, and clammy, you might become nauseous or even vomit. You may have some muscle cramps, and your pulse will be rapid and weak. So that's sort of the main symptoms for heat exhaustion. If that's happening to you or someone you know, get yourself or them to a cooler, air-conditioned place and rest. Make sure that you're drinking lots of water to stay hydrated. And also things like cool showers and cold compresses can help lower your body temperature to bring you away from this threshold for heat exhaustion. If those precautions aren't taken or they're just insufficient because maybe they're too late, the individual may progress toward heat stroke, where the faintness and dizziness may convert into a throbbing headache or even a loss of consciousness. Big signs in terms of people moving into heat stroke is that they will stop sweating. So they'll move from excessive sweating to no sweating at all. Their skin will move from cool and clammy to hot and red and dry, and their body temperature is going to start to spike as well. The nausea and vomiting may continue, but the pulse will actually shift to a stronger pulse. And this is the point at which professional medical attention is needed. So call 911 if these symptoms are occurring for heat stroke. But again, this can happen across the urban to rural continuum. If you think about outdoor workers, agricultural workers, and farmers, this can be a significant challenge because they're outside for long periods of time in the middle of the day when the heat is the strongest. But it does mean that it is a high risk to the general public. And it isn't just a matter of whether or not you are sick or not. Weather-related fatalities in 2023 in the US, according to the National Weather Service, we had 207 heat-related weather fatalities in the US in 2023. That's the national official numbers. And you can see from this graph on the left that heat is the #1 weather-related fatality year after year, both in 2023, the 10-year average, and the 30-year average. Far and away is the largest threat to human life. Even above flooding, tornadoes, hurricanes, heat is the #1 killer. However, at the same time, different parts of the US have begun to take a more nuanced and detailed approach to how they're defining those heat-related deaths. And so in Maricopa County, which is where Phoenix, Arizona is located, they looked at their death records for 2023, and they looked at it over the past decade or so, and they have continued to see a steady increase, alarming increase in the number of weather and heat-related deaths in the county. There are approximately 5 million people living in Maricopa County, and they had 645 heat-related deaths in 2023 alone. So if you look at that number, that's 3 times what the national statistics are. And I was recently in New York and heard from someone in the mayor's office in New York City. And in 2023, they noted about 350 deaths within New York City alone. So between just those two, albeit major cities across the US, that's closer to 1,000 people have died from heat-related deaths, as opposed to the national numbers. So the national numbers are undercounting, which means that the risk is even higher across the country, including in the Southeast. So I will briefly mention that it does also translate to not just heat health related outcomes, but we can also begin to see impacts on our mental health as well from the heat. So this is a paper that I published a couple years ago, where we looked at schizophrenia in Phoenix and hospitalization records. And what we were able to do with this is that we were able to identify that the number of hospitalization admissions in Phoenix, Arizona that are for schizophrenia, but can be attributed to the overnight air temperatures, resulted in a total healthcare burden over a 9-year period of over $26 million in 2024 USD. So we're seeing it in terms of heat stroke, heat stress. We're seeing it in terms of heat-related deaths, but we're also seeing impacts on our mental health that is translating then to dollars spent by our healthcare system on what I would consider preventable hospitalizations and preventable deaths. We could save 26 million and we could open up a lot more hospital beds if heat was not playing as big of a role, temperature was not playing as big of a role in our mental health. So how do we then get from that high level, all these heat related issues, into how urban areas are playing a role? So here we're getting into this crash course a bit. So this is a couple of images from a textbook called Urban Climates. Essentially, when we put an urban area over a previously rural area, we add in a few more terms into the surface energy balance. So as heat comes in from the sun, the plants are going to absorb it. They're going to use water to grow and to move through those agricultural cycles. But when we put a building or cars into those areas, we're adding in a few more parameters. So the key parameters that we've added to the system are what we're calling Q sub F, which is down there in the very bottom equation. It's also what we would consider, we call it anthropogenic heating. And so it's oftentimes is being connected to things like waste heat from cars, waste heat from industry, or maybe from your HVAC systems in your home. All of them are producing extra heat and adding that to the urban system. And collectively, as these materials and point sources of heat combine, we end up with warmer conditions in the urban areas relative to their rural counterparts. So essentially, all of that comes together in what we call the urban surface energy balance. So all of this is trying to balance out the sources of energy and the releasing of energy from different sources and areas. So obviously we still have the sun is playing a role in urban areas and in rural areas. But our urban materials, such as the roof, our roads, particularly asphalt, brick walls, and other types of walls, all of them are absorbing the heat from the sun and then releasing it at different rates. Particularly much slower rates than what we see from trees and grass and open areas. Particularly when you put buildings closer to each other, as they release heat, that heat then starts to bounce off the other buildings, as you can see in the images on the right. The top one is during the day, where there's a lot more complexity going on because you have the sunlight coming in and the buildings and material releasing heat. But because of all of this, we have to do energy balances in the urban space for our roofs, our roads, the open grass that might be there, and walls. We also have to track energy balance of the buildings themselves. So our buildings, we oftentimes are using air conditioning to accomplish this. So we maintain a more comfortable temperature indoors by using some sort of mechanical air conditioning, but that extra heat has to go somewhere, so it gets removed from inside the building and blown out into the outdoor areas surrounding those buildings. We can also look at this in terms of the height to width ratios of different buildings within an urban space and what we call an urban canyon, where we've artificially created cliffs that are our building structures themselves. So all of this comes together in what we call the anthropogenic heat flux. So these figures on the right are a couple of different examples of how our energy usage in our buildings play a role in the total amount of heat that we're adding to the urban area due to our mode of life in urban areas. So whether we're heating or cooling our spaces, trying to use energy for basic electricity, as well as variations in how frequently we use said energy or electricity can play a role. So this first figure in the top left of the three, as temperatures warm up, we lower our heating demand, and then we sort of have this neutral space where there's a base load, which is essentially what it costs to keep the lights on, to keep your refrigerator running, etc. And then as you move past that neutral state, you start increasing your energy consumption because you're starting to use air conditioning or some form of cooling. So that increase in the cooling side of things is not as drastic as our heating demand in the colder months of the year, but we do still see an increase in that demand. And so if you go to the next figure next to that, you can see that particularly in those winter months, our electricity in the high latitudes tends to be more dominated by the winter months rather than the summer months. Traffic stays pretty neutral, but our natural gas and our electricity both tick upward as we move into the winter months. We can also see this across urban areas. So this is at the bottom here, just a couple examples from Toulouse in France, where we can see that in the heart of the city, in the center of each of the images, both in the summer and the winter, we see a concentration of heat. In the winter, it's a little bit more decentralized because there's a lot more heating demand in those winter months in France. But we do still see additional heat being expelled by the buildings through anthropogenic heat flux in the urban areas relative to the rural areas. And we can look at this across different densities of populations. And we can see that places like Atlanta and Chicago on the right here, their winter and summer patterns in terms of anthropogenic heat do vary quite a bit. The x-axis here along the bottom is giving us time of day. So you can see when people get up, you see an increase in anthropogenic heat flux. It drops down in the middle of the day and then peaks again when everyone's making dinner and comes home from work, and then drops back off at night. The difference is for a place like Chicago, that heating demand in the winter is a lot higher than the cooling demand. However, in places in the Southeast, the heating and the cooling demand are pretty similar in terms of anthropogenic heat. And so in the summer months in particular, we are continuing to expel heat at a pretty rapid rate in the southeastern parts of the US, and we're not getting any benefit from that. We don't want it to be hotter outside as we're trying to keep our air conditioning on. Whereas in the winter, you know, it's kind of nice when you add some extra heat through that electricity and anthropogenic heat consumption and flux, because it warms up the urban areas when it's a little bit colder outside. So that's sort of the anthropogenic heat side of things, but we also know that wind plays a role in all of this, and our buildings are modifying our wind flow. So this is a great example of how wind flows over the condos on the Gulf Coast and creates sort of vacuums behind the condos in the inland parts of the Gulf Coast. So with this, we know that that wind flow can help cool things off, but if our buildings are blocking that airflow, we can end up with more stifling heat behind the building. And so that's what the images on the left kind of give us examples of how wind patterns flow as we reorient our buildings, or as we look at it from a top-down view or from a side view. And as we put our buildings closer and closer together, we start to see an impact on our wind flows. The closer the buildings are, the less wind actually gets down into where people are walking in between the buildings. And so it can create more stifling wind flow as the air moves over the tops of the buildings, but doesn't actually make it all the way down to the surface underneath. So we get these small eddies within the urban canyon where we're not getting a nice exchange of fresh air, we're just sort of recycling the same air that we've already been breathing in and dealing with that waste heat. It gets trapped more easily as those buildings move closer to each other. So our spacing of our buildings plays a big role. And also so does the intersection of our streets. So depending on the orientation of our streets relative to the wind, we can end up with different patterns that can improve or exacerbate both the trapping of heat as well as the trapping of our air quality issues within the city. But as we move from urban areas where we have a rougher surface because of all those buildings and move towards smoother areas like oceans or prairies. Crops sort of sit in the middle here. What that does is that it actually creates slower wind speeds in the urban areas. So we're actually reducing the amount of airflow that's getting into the middle of the city that can then allow for that heat to be removed. So because of that, it then continues to further exacerbate the trapping of heat in urban areas. So that gets us to essentially what an urban heat island is and what it looks like. So across different conditions, daytime versus nighttime, different wind flow patterns, et cetera, we can see slightly different patterns to our urban heat islands. But in general, what we do see is that an urban heat island, whether that's your surface air temperature or your surface temperature or your air temperature, both of them are more elevated in the downtown areas. But our surface temperatures are going to respond the most during the daytime because they're absorbing all of that extra heat. Whereas at night is when we typically see the biggest difference in our air temperatures in the urban areas versus the rural areas. So that's part of why oftentimes your cities are going to have less frost or snow falling at night relative to the rural areas, is because these materials are keeping things warmer at night, both air temperature as well as surface heat. Whereas during the day, your air temperatures might only be slightly warmer, but your surface temperatures will be drastically warmer during the daytime. And that plays a role in terms of building out our wind flows across the urban area. That heat will then begin to rise in the middle of the city, creating what we call a country breeze that brings in cooler air from the outskirts of the city and the rural areas into the center part of the city and create this urban dome. This can then make some impacts on our wind patterns, but also our precipitation patterns. All of this, though, is dependent on location and wind directions around you. So on the left here is just a few different examples of how those wind patterns and heat can be trapped over the built-up areas and look a little bit different in different contexts. And ultimately what it does is that it actually raises the boundary layer of our atmosphere over cities, which then translates into more mixing within the atmosphere, which can also be helpful for the production of our daytime convection thunderstorms, and sometimes can also then result in differing precipitation patterns across the urban-rural continuum. So all that to say, we end up with a lot of trapping of heat within our urban areas because of the materials, because of the extra waste heat of our HVAC systems and cars and people as well, emitting extra heat as we walk and sweat and have our own metabolic functions. So how can we actually address some of these challenges to make things more comfortable for us? So I'll briefly talk about both shade and green infrastructure, and I'll just mention initially that shade is helpful, but not all shade is created equal. This is from a paper in Phoenix, Arizona, with a somewhat kitschy name of 50 grades of shade, but it does describe well what we're talking about. We're looking at different types of shade and how beneficial they are to reducing heat and making things cooler. So in this paper, they looked at engineered shade, things like umbrellas, pergolas, shade sails, or things like PV panels that create canopies. They also looked at shade from buildings themselves, like breezeways or overhangs, and then also looked at natural shade, how different types of trees play a role. And what they found is that all types of shade are helpful, but our engineered shade can actually be a more beneficial type of shade in different contexts. Now, I will mention that we're talking about here Phoenix, Arizona, which is dry heat. But even there, they found that shade from engineered or urban forms tend to be slightly better at direct benefits to air temperature than our natural shade. This is just another slide from that as it breaks it apart into those different groups. And you can see that the urban form on the left here is providing the lowest or the largest amount of cooling, whereas your engineered lightweight and like engineered structures like shade sails, sometimes better, sometimes worse, and the natural stuff is sort of in between the vegetation. So all of that then gave them ideas on in places in a dry heat as to what is most beneficial. If we think about that in the southeast, where we also have humidity to deal with, the introduction of more trees can become a problem because we're adding extra humidity to the system as well. So what does that green infrastructure do for us? In the case of Louisville, Kentucky, so on the edge here of the Southeast Climate Center, this is a paper from 2019, so it's a little bit older, but they noted that we see urban heat as a way to plan our cities in a more adaptive way, where typically we tend to see the hotter parts of the city are places with less green infrastructure, as well as typically lower socioeconomic conditions along the way as well. But they do note that these then provide us sort of with targeted areas that we can focus in on in terms of where to implement green infrastructure or engineered infrastructure as well. And on the right here, they simply note that as they look at combining different strategies, such as combining green infrastructure with gray infrastructure, cool roofing, cool pavements, as well as planting trees, that they can see some big benefits that are happening, both in terms of reducing the daily high temperature on the panel on the left, and the reduction in the overnight temperatures really centered in on the CBD, the central business district, down toward the airport, and in the western portions of Louisville, Kentucky, near the river. So combining those two can make a big impact in concentrated areas, particularly on those nighttime temperatures, which again is where we see the urban heat playing the biggest role. If we look at Atlanta, Georgia, this is a paper that was published in 2022, looking at remote sensing across Atlanta, Georgia, to look at heat exposure and how that relates to the normalized difference vegetation index, or the NDVI, which essentially tells us where is there healthy vegetation and where is there not vegetation or unhealthy or dead vegetation. And we can see that the heat through the land surface temperature is inversely correlated with the NDVI, meaning that places with vegetation have lower surface temperatures than places without that vegetation. So again, if we think about our cities, they're going to be hotter. We're seeing that happening, but we can also begin to identify at using remote sensing, for example, just how much of a difference we might begin to see when we start putting in vegetated canopies. So they also looked at this in terms of sociodemographics, and they found that NDVI in particular is negatively correlated with socioeconomic variables. So that means that for lower income individuals, they're usually in places with a higher, lower income with lower vegetation amounts or a lower NDVI. Higher NDVI typically associated with the higher income, as well as various other factors such as education, more highly educated. The percent African American also is another space where we see differences in this paper and in this research, where the block group in the census are higher percentages of African American, we see a decrease in the vegetation in that area and an increase in the impervious surface as well. So briefly, I'm going to share just some new updates from some of my work in Singapore, where we looked specifically at a park within the city to explore how this might be playing a role in providing cooling to the city. So on the left-hand side, the three images to the left of the solid line that I've sort of drawn through the middle here, we can see how under a cool day in Singapore, which is really actually not that cool, but it's close enough, that we can see some benefits from the vegetation of the park, which is sort of in the center here. The white is all buildings, and then the green areas are cooling. in a hot day, which is truly hot, we're talking 34 Celsius, which is looking at about the mid 90s for the air temperature. And we're looking at 60, 70+% relative humidity throughout much of the day. So incredibly uncomfortable times of the year in the middle of the day. That benefit is really only restricted to the park itself, and doesn't reach very far into the surrounding neighborhoods. Now, some of this has to do with even lower wind flow in Singapore, but we also know that it's a very humid place with a lot of vegetation, so that those trees are doing a lot in terms of evapotranspiration as well. That is slowing or minimizing how much cooling we can actually get from our trees. So some concluding thoughts and key takeaways as we think about the impact of our buildings and urban heat. So buildings are a crucial component of the urban system that stores heat, and we can't get rid of them. But we can think about the size of our buildings, so how tall or how narrow the streets may be can provide some more issues along the way. And with that, I will wrap up and toss it back to Chris.
Hi, I'm not Chris, I'm Meredith. Thank you so much, Peter, for that really informative overview of the drivers of urban heat and some solutions. It's incredibly relevant to the Southeast. We've had a number of conversations in this webinar series related to extreme heat as well as urban heat islands, and that will continue to be an important topic for this region. My name is Meredith Muth. I work for NOAA's National Integrated Drought Information System, one of the organizers of this webinar series with the Regional Climate Center of the Southeast and the National Weather Service. We're just about out of time. I have one question that I am going to go ahead and pass to Peter. And again, if I don't have a chance, I just want to thank so much to all of our speakers, our regulars, Chris, Todd, and Pam, as well as our guest speaker today, Peter. I'm going to go ahead. It just came in. You know what? This is a long one, so I'm just actually going to email this one to you. And it would be great, Peter, if you could respond directly to the person asking this question.
Yeah, definitely can do that.
That would be great. I just want to be respectful of everybody's time, and I want to, if you have any other questions, go ahead and shoot them in and we will get to them offline. Absolutely. I do want to flag for you that we do have a couple of webinars coming up, a new tool from the Weather Service to look at water prediction. And then in September, we're going to hear about a fire tool, fire weather portal that's recently been expanded from North Carolina to the Southeast. Some really excellent work that's being happening in the region. As a reminder, we will email you the webinar recording, and key takeaways will also be posted online on the U.S. Drought portal, drought.gov. And lastly, a webinar, post-webinar survey will pop up. It'll take 1 minute to answer. If you haven't done it before, if you have some ideas of topics that you would like to hear about, go ahead and let us know, and we'll go ahead and we'll do our best to have that as a special presentation in the future. And so with that, again, thank you so much, everyone, for joining us this morning, and we look forward to having you next month. And thank you again, speakers.